The coming decade will see major changes and innovations in vehicle architectures, in the automotive industry, to drive the future of connected, autonomous, service-oriented and electric driving. After decades of incremental revisions, vehicle architectures have reached a breaking point, because they cannot easily scale or meet future requirements. Therefore, a shift is taking place, from a hardware-defined approach that had specialized electronic control units to a scalable, software-defined approach, with functional consolidation. Stronger processing power and higher speed onboard networks are needed to handle the huge increase in sensor and vehicle-generated data. New services driven by vehicle data also require high-speed centralized data access, as well as application processing, and end-to-end security, between the vehicle and the cloud. With higher levels of autonomy, the need for functional security also increases. Successful integration of these new approaches and technologies is a prerequisite for long-term success. Domain and zone-based vehicle architectures are gaining ground as a foundation in supporting ECU consolidation and software-defined vehicles. Domain architectures focus on the logical optimization of the vehicle. Domain controllers are used to enable high-level control. These also help a new software platform grow and consolidate the number of ECUs. Zone architectures, on the other hand, focus on the technical optimization of the vehicle, in terms of their position. They reduce the length of the wiring harness, with technically sensitive network topologies, and zone controllers that consolidate adjacent ECUs. Both architectural approaches will overlap in the future, meaning that logical and technical optimizations will be used in vehicles in the future. These optimizations reduce the wiring effort, the associated costs and the weight. They also decouple hardware and software, and as a result support more software-defined functions. But the new architectures also lead to new challenges. These architectures rely on high-performance processing, with gigabit Ethernet for backbone communications, and in-vehicle legacy networks for central compute, gateway, and ECU consolidation, to support existing ECUs during a transition period. Automotive Ethernet, with time-sensitive networking, enables reliable data flow with low latency, guaranteed bandwidth and time synchronization, which are essential for real-time automotive applications. This requires the use of new automotive processors, connected to multiple gigabit Ethernet and legacy interfaces, providing both real-time and application processing, to support ECU consolidation and vehicle services. These new processors must support advanced software technologies that provide isolation and freedom from interference between independent functions. This includes support for trusted and untrusted, and critical and non-critical services on the same processor. As the level of autonomy increases, and critical vehicle functions are integrated, support for functional safety level, ASIL-D according to ISO 26262, becomes important. This applies not only to the design and development of chips, but also to the critical software that runs on them. There is a shift from fail-safe to fail operational systems, to enable some level of operational functionality, through redundancy with fault detection and recovery mechanisms. To meet the challenges of EE evolution in vehicle architecture, NXP has taken a new approach to in-vehicle data processing. This combines automotive, enterprise and safety technologies for the S32G2 family of vehicle network processors. S32G2 processors are designed for SLD safety-level applications, with integrated hardware and fail operational mechanisms. They also offer support for the power management IC and a safety software framework. This provides an interface to the safety hardware and optimizes the development of safety software. Due to their scalability and combination of functions, vehicle network processors are used in automotive applications to address new architectures including service-oriented gateways, domain controllers, zone processors and safety processors. The next decade will see serious changes in EE vehicle architectures as they move to domain and zone architectures. These will usher in a new era of software-defined vehicles that can add significant value and make the case future a reality. There will be challenges along the way, but the automotive industry will collaborate to overcome them. These processors will help address key challenges and support vehicle-wide deployments to enable vehicle architects to develop compelling new vehicles.